court of public opinion. So it is a privilege to introduce Dr. Brabson. We did meet each other, I think it was almost 3 years ago, at a seminar that the church Trinity Fellowship hosted, but in cooperation with Michael Hamburger and several IU scientists. And that was an incredible event, and we began working on this shortly thereafter, and it got interrupted by COVID. Dr. Brabson is Emeritus Professor of Physics and Climate Science. Am I getting that whole title correct?
More than enough.
Okay. At IU. Also chair of the Climate Committee at Trinity Episcopal Church in town. And more than any of that, he is one of the true gentlemen I know. I aspire to be as kind and gentle. When I get an email from Ben in my inbox, I'm like, oh, good. I get to open an email from Ben because it's always encouraging. And so I'm just thrilled that he was able to find time to be with us this morning and share his knowledge with us. So Ben, I will hand it over to you and give you as much. We have about 45 minutes to 50 minutes left in the hour. So thank you, Ben.
Dan, you're a marvel. All those things apply more than equally to you. It's such a pleasure to have you on the other end of that email, and I just greatly appreciate having a chance to talk to you. I don't know many other people in this room except Mady, and Mady and I have worked together over the years on other projects, and I am delighted that she is here and that you're here. So it seems to me my objective this morning is very simple, and that is to understand and learn from you. The first thing I've learned already is that it's a wonderful way to start an adult Sunday school class, that is to have highs and lows. I've never known how to do that before. And it works beautifully, and it gets all of us thinking about other people, and that's where we are. So this is item number one. Most important thing I've learned this morning already is certainly that, and I look forward to other things that we will learn from this discussion. So the other thing I can do as a climate scientist is to remind us that the climate really is changing. If you have any significant doubts in your mind, I think I can allay those doubts. I can put them aside. The answer is things are changing. They're changing more rapidly than we hoped or we thought 10 years ago, so things are not pleasant. So I can depress the heck out of you by presenting information. I will do that to some extent because it's important that you can see what is happening, not necessarily only here in Bloomington and in Monroe County and in Indiana, but also a little bit of what's happening outside in the world, and it's not all pleasant. And it's having to do with everything that has to do with increasing temperature, but also lots of things that have to do with water, that have to do with soil moisture, that have to do with extreme temperatures where people can't survive. There are actually places now on Earth, on occasion, when people simply cannot survive. That's not good. So we need to worry about that, and the nice thing is that the good thing is that we can do some things about that here, locally. So there are two pieces. I have the great pleasure of having you here this week and next, and of course I can drive you away so you don't come back next week, but if I don't manage to do that, what I'd like to do is to spend this time, let's say half an hour, and then well, better than that, let's do this. Let's just say anytime something interesting or abnormal or different occurs to you, or not, just speak up. Just say, wait a minute, Ben, that doesn't make sense. I heard differently, or I'm concerned about that, or can you say a little bit more about that, or whatever, and we'll just stop and have the discussion right there. At the end, I'll certainly leave a good 10, 15 minutes at the end so we can just sit quietly and think about what to do. So the first day, today, I'd like to talk about the science and about the technical solutions to the problem of climate change, some of the technical ideas. And then next week, I'd like to talk about some of the personal responses, if that's okay. So that we can mix and match, but that's the idea. Okay, so I start by entering my password, right? Okay. Right. That's great. Right. Hope I can remember. It worked. Okay. Now I can do one more thing, and that is I can do here. Okay. That's just a silly joke. Okay. Okay, so I think I can go ahead to the next one. All right, so I just said all those things. What I'm going to do then is to talk about the science, a couple of pieces, temperature and carbon dioxide, which are related, a couple of consequences, and then immediately move into some technical responses. And then next time, we'll talk about personal responses and something which I like to think of as discipleship, which is this idea that we as Christians we have something special going on in our lives which is a little different from the rest of the world, and that is that we are able to actually act. We actually have agency. We can actually do things based on our faith. Okay, so let's see where that leads us, just for fun. Psalm 104, wonderful. Psalm 104, a great tribute. We talked a little bit about it last time. I was listening in, incidentally, last time, so you thought I wasn't here, but I was really here. It's just I didn't say very much because I was in Albuquerque. Psalm 104, Dan read it last time, a piece of it. It just says, "O Lord my God, you are very great. You are clothed with splendor and majesty." And then talking about God, he wraps himself in light as with a garment. He stretches out the heavens like a tent. And that picture is a pretty impressive picture from Hubble telescope. It always frightens me and is exciting to know that we are part of a very large universe, and that each one of those little guys there is an entire galaxy, and this is just a tiny, tiny little corner of the universe. So it's something which is sort of overwhelming at the highest level. This is not part of the universe. That's just part of my background. That turns out to be a proton. Protons have quarks inside, and there are 3 quarks in the proton, 2 up quarks and a down quark. The up quarks each have charge 2/3, and the down quark has charge -1/3. So if I add 2/3 and 2/3 together, what do I get if I add 2/3 and 2/3 together? 4/3. And then if I subtract 1/3, 1. Ooh, what is the charge of the proton? It's 1. Good, it worked. Okay. Miracles, not miracles, but a magnificent world we live in, which is beyond my comprehension, quite frankly, and well beyond the comprehension of human beings. On the other hand, it's great fun to look. It's great fun to look and to explore. So that's what's going on in our world, exploration. Continuing with Psalm 104, there is the sea, vast and spacious, teeming with creatures beyond number, living things both large and small. There the ships go to and fro, and the Leviathan, which you formed to frolic there. I'm not sure that's the Leviathan, but that's a pretty good example of something that could be a Leviathan. If you look up Leviathan, actually you'll find it has all sorts of weird creatures and so forth, which I don't believe, but there you go. I don't know how much the writers of Psalm 104 knew, but can you?
I've always wondered if it was like the saltwater crocodile.
Saltwater crocodile, there you are, okay.
Because, I mean, they used to be huge, I mean,
Yeah.
and everywhere.
Right. But the frolicking is just, is on the way. Pope Francis said this, again, praising this magnificent world. He wrote the Laudato Si, and the first piece of that says, "Praise be to you, my Lord." In the words of this beautiful canticle, St. Francis of Assisi reminds us that our common home is like a sister with whom we share our life, and a beautiful mother who opens her arms to embrace us. Quote, "Praise be to you, my Lord, through our sister, mother, earth, who sustains and governs us, and who produces various fruits with colored flowers and herbs that of course, is a piece of our Old Testament. And there are other points of view. This is why I had a chance to go to a conference, a Mennonite conference, called the Rooted and Grounded Conference this last week. And Katharina Friesen gave a sermon a couple of years ago. This is not from her sermon this year, but from one she gave several years ago. And I just pick out something which points out that different people have different views of the same thing. And I think you will find out in this discussion that we have different views on what is called climate change. So this is called perspective shapes practice. That is, what you do in life oftentimes has a lot to do with your perspective, how you look at things. So I just read to you the first 2 paragraphs of her sermon. At one time, the confluence of 2 powerful rivers churned with such energy that they created smooth spherical stones. The Lakota people named one of these rivers the Stone Made for Themselves River, because of the round stones the river formed, which they called sacred stones. These stones are used in prayer and ceremony and are seen as an inspirited part of our relations, like the river and the plants and the animals. So from the Native American point of view, the stones are part of creation as we are part of creation. At one time, European explorers and colonizers who came to the region also saw and admired the river's smooth spherical stones shaped by the churning waters where they met the Missouri River. But instead of sacred stones, what did they see? Stones shaped like cannonballs. Instead of gifts from the river, they saw ammunition for war. And so they named that river the Cannonball River. Sacred stones are cannonballs. And then she goes on to give a wonderful sermon about this idea of different perspectives on 2 things that are really the same thing. Well, I go back then to something which is relevant to climate change and our idea of creation care. And this again comes from Pope Francis, the encyclical Laudato Si. The human environment and natural environment deteriorate together. We cannot adequately combat environmental degradation unless we attend to the causes related to human and social degradation. In fact, the deterioration of the environment and of effects of all attacks on the environment are suffered by the poorest. And then he goes on to say later, today we have to realize that a true ecological approach always becomes a social approach. So ecology and sociology are in this case linked. It must integrate questions of justice in debates on the environment so as to hear both the cry of the earth and the cry of the poor. So that's something we know, and that is that climate change, creation care in general, climate change in general, or specifically, has enormous impact on the poor, even more than it does on us. Okay, so let's talk about the science. These people are not dead. They're lying on the sidewalk because it's hot. This is April of 2018. It turns out it was the hottest April on record. Celsius temperatures of the order of 50 degrees and 122 degrees F in April is odd. You agree? So they're lying on the surface of the only cool surface around, which is on the surface which is cool, and that is the sidewalk in the shade. So that's what they were doing in Karachi. So something is going on. Well, let's look to see what happened just about a month ago. The IPCC, which is the Intergovernmental Panel on Climate Change, a good source, incidentally, if you need information about climate. It is indeed a summary of the climate perspective from the point of view of climate scientists around the world, including, I did not get involved in the writing of these volumes, but they are well conceived and have been coming out every 5 or 6 years for the last 30 years. The important point is that the science volume just came out in September, and here it is. It's on the web, and you can actually pick up a summary of it. You can pick up just the what is called the executive summary, or you can pick up, which is probably 30 pages long with lovely diagrams, or you can pick up something which is more detailed, which is a 100-page summary of the book, or you can go read all 800 pages of the book. I haven't done that, but it's something that we could all do. I just quote to you a couple of things. About past warming, it says, it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. And then with regard to greenhouse gases, it says in 2019, which was the last year for which they have data for this collection of information, atmospheric CO2 concentrations were higher than at any time in the last 2 million years. And concentrations of methane and nitrous oxide were higher than any time in the last 800,000 years. So we're talking about something pretty special. This is not just random stuff. This is stuff which hasn't been around for a long time. Okay, and it'll turn out to be, as we will find out, due to us, which is not pleasant, but there you are. Just looking quickly at global temperatures, things have been rising. These are just annual temperatures, one after another, year by year. Here's 2020, and you'll notice 2020 is not the hottest year. 2016 was actually hotter, and the reason it was hotter has largely to do with the fact that El Nino, an event in the Pacific Ocean, does tend to warm the entire middle band of the Pacific Ocean to a temperature which is high enough to increase the average by a blip upward. And so what you'll see is you can go back and pick out the El Nino years. Here they are. And in fact, those are the years when there is an El Nino. Unfortunately, there wasn't an El Nino in 2020, which is interesting because it says that, oops, we're getting to the point where we're getting high temperatures and there isn't an El Nino.
So
That's not a good situation. Question.
Is it measuring ocean temperature then, or average air temperature?
This is air temperature.
This is air
Let's go on to
temperature.
ocean temperature next. A brilliant point. Ocean temperatures are extremely important because, of course, the ocean is actually absorbing more than 90% of the temperature of the heat coming in from the sun. Okay, why is that? Well, the ocean is bigger, it's blacker. If you have a black ocean, it absorbs lots of sun's energy, more than the land. What color is the land?
Green and brown.
Sort of greenish and brownish stuff, yeah. And sometimes it's like deserty stuff, which is pretty reflective, actually. So the ocean is a really good absorber and ultimately absorbs more energy than the land. And so equally important, maybe even more important, is knowing the temperature of the ocean, which is also rising, okay? Okay, so looking just back at temperatures over the last, these are air temperatures now, over the last 1,000 years, 1,000 years. Here's that little plot we just saw where we had the rising, and let's go back for a moment. What I just showed you was that little piece right there, that little stick right there of rising temperatures. Here is 2020 right here, and you'll notice that there was a medieval warm period when Greenland was settled, and then there was the mini ice age when things got cooler, and then there's the 20th century when things went up, and then there was sort of a flatty piece in the middle, and then this piece at the end which has been rising, and there we are, okay? So something funny is going on, all right? This is not standard. If it were standard, it would look more like this. Wiggle, 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 maybe with some medieval warm periods and some mini ice ages and some more wiggling over here, but that's where we are, so that's weird, okay. So, a moment to reflect on higher temperatures. Are you happy? Are you sad? I mean, should we just cry? What do we do? Do something about it? Shall we dig in? There are obviously some wonderful things that happen because of high temperatures. Better swimming, you can, if you live in Russia, or if you live in Canada, what are Canadians thinking right now? Yes! Unfortunately, they also do other things. High temperatures produce desert and desiccation, drying of land, which is very, very serious. Okay, the other piece of the puzzle is carbon dioxide, and I'm going to talk just a tiny bit about carbon dioxide. That's a picture of radiation from the sun. I'll do this very quickly. This is visible radiation. This is the stuff you can actually see. We see lots of radiation in the visible from the sun, a little bit of ultraviolet over here, and then this huge band of what is called infrared radiation. And that's the stuff that you can see in an infrared camera. Have you seen it? Well, I'll show you an infrared camera. There's a picture of Cynthia. I shouldn't, it's good she's not here. She wouldn't. That's a picture of Cynthia taken with my infrared camera, not my infrared camera. And you'll notice that her neck temperature is just about 37 degrees Celsius. Interesting that 37 degrees Celsius is 98.6 degrees Fahrenheit. So what's your body temperature? Oh, 98.6, always. Well, that's what we were told. It's not really 98.6, but it's close. So interestingly, your neck temperature is often awfully close to your inside body temperature, which is an interesting way to test. Also, your forehead, as you know from all these people who are shooting infrared guns at you all the time, your forehead is a good measure of infrared temperature. Okay. So infrared radiation is saying basically that you're glowing. You are a glowing object, a wonderful glowing object. I can close my eyes and I can find you just by holding my hand up and not even touching you. I can just get up close to you and I can feel the infrared radiation on the back of my hand, and you could do that too. If you put your hand up like that, you can actually begin to sense the infrared radiation coming from the two good detectors, namely your forehead, which is a good detector, also the back of your hand is a good detector for infrared radiation. Okay, so infrared radiation, this I will probably skip, but this is the input of energy from the sun in the visible, and then out here is the Earth trying to re-radiate that radiation away from the Earth, and there's a little window over here which is filled with, unfortunately, carbon dioxide, nitrous oxides, and some of the ozones in the middle. So that little window is important. This window is nice and open, so lots of energy comes in through that window, that's the atmosphere, and less of it gets back out again if you tend to close this window off. And the way you close that window off is by adding carbon dioxide or nitrous oxides or any of the other greenhouse gases. So what you don't want to do is to keep the Earth from cooling off. Heating the Earth is easy. Or if the sun comes in through the atmosphere, it's doing so right now because it turns out the sun is coming out, which is very nice. Sun comes in, warms the surface of the Earth. Basically, it goes right through the atmosphere. It does warm the atmosphere a little bit, but basically it comes through the atmosphere, warms the surface of the Earth, it gets warm, and re-radiates. Warm bodies radiate. You radiate, the Earth radiates, and gets rid of its excess heat. Fine. There's only one thing that gets in the way of getting rid of that excess heat, and that is a blanket on top of carbon dioxide, for example, which absorbs that radiation and re-radiates it, some of it down and some of it up. Not all of it. It doesn't all go back down again. It's like a blanket on your bed. Some of the heat indeed stays with you and some of it actually does escape. But by putting the blanket on top of you, you do increase the temperature in your, next to your toes, right? That's the whole point. Okay. Okay, so what's going on with CO2? Well, CO2 is rising. You've seen this before. That is simply an increase in CO2 over the last 50 years, 60 years. And here it is on a daily basis, and you can see that yearly basis, and you can see that month by month CO2 is rising, and there we are right now. That's September, and if I put October on that map, where would you suppose October would be? Well, October, it looks like there's September of last year, there's October, and there's November, December, January, February, March, April. So it looks like all winter CO2 increases, and all summer it decreases. And that's a great mystery, isn't it? Because we don't understand why the CO2 goes down in the summer and up in the winter, do we? Why do you suppose CO2 goes down in the summer? Who's out there
Warmer?
absorbing CO2? Good idea. It's warmer. What else is happening in summer? Trees, yes. What are the trees doing? The trees are absorbing the CO2. All summer long, trees are eating the CO2. Yes, good. All winter long, trees are not doing their job, and they're increasing. I'm being a little silly here, but there is winter and here is summer. So good summer, winter increase, and we'll go on. Well, all right, CO2 then, again, is here, and you can see that there's 800 years, 1,000 years, 1200, 14, 16, 1800, and here is the beginning of the Industrial Revolution. And what you see happening here is not the 280 parts per million standard stuff, but something is going on here which is increasing the amount of CO2. Largely that's coming from the burning of coal, it turns out, because coal was the principal resource used in the 19th and 20th centuries. And you can see then as we continue to burn fossil fuels, that number goes up. That's that same line that we had on the last graph. And there we are again, 417 parts per million on average right now. Question?
Can you briefly just explain how we got those parts per million numbers from times when we weren't measuring the parts per million? Is that coming from?
Sure, no, brilliant, good thinking, yes, how, this is easy. This is the part where we have Mauna Loa and it's sitting there with a CO2 detector and so forth. So how the heck do you get CO2 measurements from 1,000 years ago, or 10,000 years ago, or even 100 years ago? Interesting detail. Let's suppose that you look at, well, here's the easiest way. The easiest way is to look at ice in Greenland or in Antarctica, and you take a chunk of ice, and you find there are bubbles in the ice, and you can extract from those bubbles in the ice the air in those bubbles. Okay? So far, so good.
Like
One
we
thing you can do is
understand.
simply look in those bubbles to see how much carbon dioxide there is in the bubble. Ah, that's cool, because I can simply measure the fraction of each bubble, which is now CO2, going back year by year by year over the last 10,000 years, and before that over the last several 100,000 years. So that's the easy way to do CO2. It turns out in those same bubbles you can get temperature as well, but I'll ignore that for the moment. So direct measurement of CO2 is pretty straightforward. Namely, look at the bubbles, calculate the fraction of that bubble of air, which is a fraction of that which is regular air and which is CO2. And if is it normal or not? What is normal? Well, normal is this famous 280 parts per million we were talking about earlier, which has been around for the last 10,000 years. Here, what does parts per million mean? Well, it means if you start counting molecules, you will find that out of every million, you get 280 that are CO2 molecules. Is that okay?
Yeah.
Okay. Okay, so what happens? Well, we anthropogenic folks, that's human-produced CO2, mainly is coming from burning fossil fuels, 90%, and about 10% comes from land use change, where you're cutting down forests and doing other things. And where does it go? Well, that 100% over here goes roughly half into the air, a quarter into growing trees, and about a quarter into the ocean. This is the piece we're worried about here, because that's the part which is acting as the blanket of CO2. The part that's going into growing trees actually could be viewed as being positive, because you're getting more rapid growth of certain kinds of trees. You may be getting more rapid growth of certain vegetables and fruits and grains. One can argue about whether the actual input, the value of the grain that is growing is better, but the fact is that CO2 is doing some carbon fertilization. In the ocean, of course, it's again negative because it tends to acidify the ocean. So that's basically what's going on. We summarize that piece then by saying this. Our available fossil fuel resources are huge. It turns out we have enough coal alone to run the world at present rates for something like 200 years, 150, 200 years. Plenty of coal. Here in Indiana, we have enough coal to run our state of Indiana at present rates alone, if we just simply stopped using natural gas, stopped using oil entirely, and simply used coal, converting it to oil and then to natural gas for all sorts of heating purposes, we could run the entire state of Indiana on our coal for 400 years.
Wow.
We have a lot of coal. Right. So that's what we have, okay? Land use change is happening rapidly. Indonesia is 54% forest, or was a few years ago. It is now much less than that. Climate change, unfortunately, is very incremental. It's long-term, and it's sometimes hard to see. And the damage from climate change is enormous, but oftentimes difficult to identify. Okay, so enough science. Are we okay? Because I want to make sure that you understand that it is happening, and it is happening we can look at the details. We can look at all the different gases that are increasing. Nitrous oxides are increasing, CH4 methane gases are increasing, CO2 is increasing at record rates and so on. So are we happy with the science? Not happy with the science. We're unhappy.
No.
Okay, so let's talk about some consequences and then some responses. Consequences are several. One is that we have present drought in the US. Of course, there was a wonderful rain that took place this last weekend. This is a picture after the rain, so you can see this is no longer black. Over here in Los Angeles, they had more than 3 inches of rain, which is magnificent, and they're greatly blessed for that, and we are enormously fortunate that took place. Nevertheless, a good portion of the West has been in drought condition for several years and seems to be on a trend to stay in drought condition, which is not good. That is, climate change seems to be projecting that things will stay dry in the West, and that is not a good situation. If you look at Indiana, our old friend Indiana, and just look at temperatures here, you'll see the temperatures in Indiana year by year are very, very variable. But if you look at the average over the last 150 years, 120 years is going up, and the average over the last 60 years seems to be rising even more rapidly. So the question is, do we really care? I mean, this is a rise of about 1 degree Celsius over the last 100 years. Does that have an effect? Well, one of the effects it has is a very good effect in the sense that you can now grow crops you couldn't grow, plants you couldn't grow before. If you look in 1990, we were deeply embedded here in Indiana, or almost deeply embedded in this dark greeny section here, which is zone 5. So we were viewed as being in zone 5 from the point of view of plant hardiness. So if you're a gardener, that's very interesting. But notice now in 2015, or now later than that, this happens to be 2015, we are no longer in the dark greeny stuff. We're in the light greeny stuff, which is now down here at zone 6. So if you're a person who likes to grow crops, then who likes to grow flowers and things, you should pay attention, right? So anybody here notice over your own lifetime any significant changes in climate, or is that just too general question? I certainly go way back and can remember being here in, being as a kid, going out sledding on a regular basis in the wintertime with lots of snow in northern Ohio. I was brought up in Findlay, Ohio, not here, but I remember that thinking that the number of days when I could actually go sledding was pretty large, and now I'm not hearing that or seeing that from
Even
my
30
friends who
years
live in
ago.
Italy. So that's my sense, and there's the things, even at the fundamental level of feeling and noticing as human beings, where we're doing something which is really not very scientific, it's still clear that things are changing.
I have a quick question.
Yeah, please.
On that map that you just showed,
Yes.
So that's amazing to me. I mean, I'm looking at the differences there.
Huge.
But I'm wondering if you went back, 25 or 35 years,
Yes.
would changes be kind of at that same rate? Like if you looked at a map from 1960, would you continue to see those sort of shifting? Like, I'm just kind of curious.
Very
That's
good
a more
point.
modern phenomenon.
Let's go back to something which is relevant to that. And, I'm sorry, all right, yes, well, it could be relevant. Here we go, all right, so let's go back from, here we are in 2015, which is right here. Here's 2015. What it did is take you back to 1990, which is back here, and you're saying, what if we went back another 20 years?
Wow.
The answer is you would still see something. If you went back beyond that another 20 years, what you'd see is that flatty part I talked about here. From here back to here, it's pretty flat, and then back at the beginning of the century was another dip that went down. Okay?
Great.
Okay, so let's here's Indiana, and then there we are. That's where we are. And the question is, where will we be effectively in the summer in 2050 if we just keep
Wow.
mulling along and doing our usual thing, and that is not paying too much attention to climate change? If none of us sign pledges and none of us start reducing our total carbon use, then Indiana will evolve, and that greeny stuff here is going to be roughly where we will be in 2050. And if we continue that, which we definitely won't do, we could end up down here at that red section down there, which is what happens if you continue to do high emissions. That is that you continued at the present rates. We would definitely move to a southern position. So, okay, so one could argue that living in Texas is not so bad, but the point is that we are changing our climate in a way which is identifiably moving in that direction. So does that affect things going on in Indiana? And this is a study done here at Indiana University, actually about now 8 years ago, by two of my friends in the geology department, Sarah Pryor and Becky Bartholomew, who have since moved on to Cornell. And they discover that indeed, if you look carefully at corn and soybeans as a function of temperature, that their overall productivity decreases. Now, part of that is due to the fact that you have to worry about the fact that higher temperatures produce also more evaporation and therefore more likely dry soils. So it's not strictly temperature that's doing it, it's temperature combined with soil moisture that does it. But the point is that increase in temperature, by and large, will create a decreasing function in productivity for the two major productions of our crops here in Indiana. This is a rather dramatic statement, but one which I quote to you. It comes from E.O. Wilson, who says this. He says, "The obliteration of nature is a dangerous strategy." Well, we're not obliterating nature, so that's a little bit over the top, but I quote on, "For one thing, we have become a species specialized in eating seeds of 4 kinds of grasses: wheat, rice, corn, and millet. If these fail from disease or climate change, we too shall fail." Now, that's a very dramatic statement, but I put that out there because we are in a kind of dilemma. On one hand, we have sufficient-based fossil fuels to run our society at or above present levels for at least 150 years, here in Indiana for 400. On the other hand, to do so will drive up the Earth's surface temperature to a level sufficiently great to reduce its carrying capacity. Now, that's a different statement. Let me reread that. It's not just that, all right, so there's a slight decrease in corn and soybeans here in Indiana if it gets warmer. Do we really, really, really care? Because some clever person is going to figure out a way to increase that by raising the effectiveness of a fertilizer of some kind, which we haven't yet found. So is this a serious problem? And if it weren't for the fact that we in Indiana actually export food to the rest of the world, it wouldn't be a problem, but we do. We do export food to the rest of the world. That means that we're reducing the capacity of the world as we increase temperature. That's not good. Yes?
And it's also worth noting that those fertilizers that are being used are all carbon-based fertilizers that are actually making the problem worse. Right?
Most of those
So-
fertilizers, essentially all of those fertilizers are climate-based. Just to scare the heck out of me, this you don't have to look at this, but I just look at this myself. This just reminds me that there are circumstances under which human beings cannot survive. That turns out to be your body temperature again is what? 98.6, which in degrees Celsius is 37. Okay. It turns out that if the wet bulb temperature, and I'll explain that in just a moment, the wet bulb temperature rises to 35 degrees, that's 2 degrees below your body temperature, your body can't cool itself anymore. You have to have a wet bulb temperature which is below your body temperature in order for your body to function. Now, ordinarily you say, wait a minute, I can stand outside and it's 110 degrees outside and I'm fine. That's true, but that's dry bulb temperature. That means that that's the amount of temperature. There's a huge amount of evaporation going on if you're out in Arizona and it's 110. No problem. Your body can immediately cool by evaporation of water. If, on the other hand, you reach a wet bulb temperature, which is very close to your body temperature, then it's like being in a steam bath at 35 degrees, a steam bath at what turns out to be 95 degrees. If you're in steam at 95 degrees, you cannot survive outside. You simply can't do it. Doesn't work. Human body doesn't function. So that's something to keep in mind. Okay, enough frightening stuff. Let's talk about what to do about this. Okay. Well, there are cool things going on in the world, and they are wonderful. And here is, I said I would leave you 10 minutes for discussion, so we'll do these quickly, but I just want to point out that some pretty impressive things. That's a bike path, and I'm a great biker. I should have biked over this morning, except I was lazy. So, bikers? Yes, yes, yes. Okay. Biking is great, and if you actually had a bike path covered with solar panels, it really is cool. This is one which exists. It's only 230 feet long, but nevertheless, it's a start. And the idea is that in Holland, they have now, in the Netherlands, they've decided to proceed with the establishment of large areas of solar panels, which are now no longer just bike paths, but also roads. And if you look at the number of road surfaces in the United States, it's huge.
Right.
If we covered all our roads with solar panels, which we're not doing, but if we did, we could supply our entire electric supply from the roads. All right? Interesting thought. We won't do that, but it's an idea. 70% of the efficiency of a normal rooftop panel, which is now up to 22% efficient, you could actually do pretty well. So, cool idea, neat idea. Large scale, small scale solar, clearly happening. I have to boast, that's a picture of our house 10 years ago, and there we are. There's the airport up in Indianapolis. Lots of things going on. Duke Energy is fully engaged. And then I mentioned one thing here, which is one of my favorite things. It has to do with the summer-winter problem. The winter's really cold, and that's really bad. I mean, it's not bad, it's really okay. And the summer's really hot. So couldn't you just take the heat from the summer and use it in the winter? Piece of cake, right? Then you wouldn't have to use fuel and all that other stuff. You wouldn't have to burn fossil fuels. Just take the summer heat and use it in the winter. Why not? Storage. Storage. So what do we do about storage? Interesting detail. Why don't I just store it underground? Just take the heat from the summer, all that air conditioning, store it underground and use it the following winter. Well, it won't work, you say, because if you heat the ground, it'll be gone by the time you get back in the winter to use it. It's all dissipated. Because if you put it in the ground, fine for the next 10 minutes, but it's gone later, or not. Interesting. Good old Okotoks in Alberta did the following experiment, just for fun. They put solar panels on all the garages. And they took this is only 50 houses, so 50 households. Took all the solar energy from the garages, only the garages, piped it into just thermal energy into the ground in a big round sphere, which is, or round cylinder, which is about 100 feet across, 125 feet across, and about 150 feet deep. And they put 100 wells into that center, and they piped all their energy all summer long in Canada into the ground. And then the following winter, they came back and extracted that heat and heated those 50 homes. And amazingly, they're able to do it now at essentially 100% efficiency. This is in Canada, lovely folks. This is not in Bloomington or in some other crazy part. So that's cool. All right. Neat things going on. I shut up. All right, now you have 7 minutes for questions.
Was it liquid or gas, or how are they storing that? What form was it in?
Interesting question. How do you store it? Big chunk of ground. Well, what I worry about is if you're a worm, you're in deep trouble. Because what you're doing is heating that chunk of earth to 175 degrees F.
Oh my God.
It's really hot.
Yeah.
And indeed, they do it in a clever way. They don't just heat it just willy-nilly. They put the hot stuff in the middle, and then there is a general cooling as you go to the edges. But it turns out that ground is a terrible conductor of heat. It conducts heat very, very slowly. Once you heat a chunk of ground, it stays hot for a very long time. So storing the energy is something which is actually relatively straightforward. This is thermal energy, not electric energy. We're not storing electricity, which is another kettle of fish. If you're storing electric energy, now you have to worry about batteries, you have to think about pumped water storage. There are other ways to do that, but it's really nice to store thermal heat. Thermal heat is something which is pretty easily done. It's been done here. Many campuses, for example, do geothermal heating and use that energy routinely. Purdue, for example, has a geothermal system where they actually heat all their buildings using geothermal. We don't here at Indiana because we're a little bit behind the times, but there you go. All right. Nice ideas, good things happening, and clever ways to do it. So we're not in deep trouble. We just need some. Well, all right. So these are. We haven't talked about cost and other things. Other questions? Your thoughts? I don't want to
Just
overrule.
storing the
Yes, yes.
actually raising the
Yes.
temperature of the
Jack.
earth.
10,000 or so years ago, we had an ice age, right?
Yes, yes.
Are we gonna have another one, do you think? Because of all this climate change?
Aren't we
That's
technically
just
still
my-
in the ice age?
I'm gonna get an iPad.
I'm just asking, I don't know.
There are several things happening. Ice ages seem to occur when the planets align, so to speak. That is amazing enough. There's more truth in poetry than that. It turns out that the cyclical behavior of ice ages over the last 8 cycles has been one where you get an ice age whenever you have a very concentric circular orbit of the Earth around the sun. Think about it this way. This is Milankovitch stuff, but if you have a very circular orbit, then you don't have much melting. What happens is you get lots of time for freezing, but you don't get much melting. On the other hand, if you have an elliptical orbit, which happens the rest of the time, so to speak, the Earth's orbit is constantly going from spherical to elliptical, back to spherical to elliptical, and it does that every 100,000 years. So every 100,000 years, you get into one of these situations where you're very circular, and then you fall into an ice age, which is unfortunate, but there you go. Right now, we're working our way back from elliptical back towards circular. So the answer is yes. We'll probably go into another ice age
If we live
at
that
some
way.
point.
Because of all the heat,
Well,
on the Earth. I'm just-
yes, but
Go ahead.
right. There's another piece of that. Yes, go ahead.
So the ice is also a big part of the current problem with this feedback loop, right? Because you were talking about the water absorbing more of the heat and the Earth reflecting it more. But as our ice fields are melting, that is also reducing the reflectivity. We've got more water, less reflectivity. So with less reflectivity, the more ice melts, the warmer it gets. The more the ice melts, the warmer it gets.
Right. Yes, that beautifully stated. You would have what is called a positive feedback situation where heating produces more heating. In most important single thing that I could say, and that is positive feedback situations are dangerous. Negative feedback situations are okay. For example, the fact that when it gets warmer it makes more clouds is a negative feedback situation, because then more heat produces more cloud, you get more reflectivity, and things go back to normal. So it's lovely for negative feedback that things go, more heat means that you actually reduce the amount of temperature because of the reflectivity of the clouds. Positive feedback, exactly the opposite. You have a situation where heat produces something that produces an additional kick in the wrong direction, more heat. There are a number of positive and negative feedback situations in the climate modeling, and it's very complicated. It looks, unfortunately, as if some of those positive feedback situations are dangerous, and we want to avoid those at all costs. And one of those could be the cutting off of the Gulf Stream. The Gulf Stream, as it works its way up into Northern Europe, can be influenced heavily by the increase in temperature of the Arctic. And the reason for that is you get melting glaciers, an increase of fresh water which is flowing back down from the north, and that heads off the Gulf Stream so that you don't get as much warm water flowing up into Northern Europe. If that happens, then you start getting a buildup of ice in the, you will simply start getting a buildup of ice in the northern hemisphere, which can indeed lead to another ice age. So the question is, what is happening to the Gulf Stream? And that's a whole discussion which we could have, but the answer is the Gulf Stream is having trouble right now. It is slowing down. It's about 10% slower than it was. The question is that due to us, or is that due to general changes in the Earth's behavior? Hopefully it's not due to us, because if it is due to us, then the people in England will be really unhappy with us. Other questions, other thoughts?
I was just gonna mention, it's interesting you would point this out, because just a week ago I was having a conversation with a friend whose husband works in the energy industry, I'm not sure where, and she was telling me about how they just this summer put in a geothermal energy efficient heating system for their house, and I was like, how does that work? I'm from Idaho, where geothermal means hot water heat.
Yes, exactly.
And she explained it was really cool, and it's not cheap, but they expect that their energy bill will be minimal.
There are, exactly, in Fort Bloomington, for example,
And
brilliant.
it's here in
Again,
Bloomington.
your name is?
Ashley.
Ashley, thank you, Ashley. The interesting detail is that there are two uses of geothermal. In the case of Okotoks in Canada, what they're doing is taking energy specifically and storing it there for the winter. What you're doing here in Bloomington is simply saying the ground is already warmer than the air,
Yep.
so why don't we just cool off the ground on a daily basis and heat our houses from the ground underneath? That works beautifully as well. So there are two different systems. One is doing a whole winter at a time, the other is doing it day by day, and they both work. And doing it day by day, good old geothermal heat pumps, is something that is very much available to us here in Bloomington. Could be anywhere, right? Very good point. Thank you, Ashley.
Could you say something about what you'll talk about next week?
Yes, let's think about next week. There is a, the question is whether or not you should be eating bananas. That's the key question. Key question.
And
Bananas.
avocados.
The answer is, of course, all of us love bananas. We love bananas. But remember that bananas have
Don't grow
some
here.
real difficulties. They don't grow here. They're not local. We don't grow. The farmer's market rarely produces its homegrown bananas. Not even close, right? Well, it turns out that's an interesting question. Is it really true? There are some nice things about bananas. First of all, they have their own covering. You don't have to pack them in plastic. Good point. You don't have to put them in cardboard. Good point. Actually, they can be shipped by boat because they're very slow to mature. If you put them into a slow-moving ship that comes up the coast. If you compare them, interestingly enough, with a quarter-pound hamburger, the amount of CO2 produced per banana is tiny compared to a quarter-pound hamburger. A quarter-pound hamburger is literally 100 grams of CO2 produced, whereas the amount for a banana is 0.3 grams of CO2. Oh, interesting. So maybe bananas are not quite so bad. Here's a story I tell you. I'm teaching Sunday school to a group of kids who are teenagers, and one of the things I had them do is to measure the lengths of their showers. Okay, our kids like to take showers, and so I said, all right, kids, I'd like to have you measure how long it takes to take a shower. You don't have to tell me exactly, but I want a good measurement. So that means you've got to, look at your watch, get in the shower, or have your mom watch the watch. Do whatever you need to do to time the length of your shower. And at the same time, of course, I had put together with James and John and Norm Crampton this little book, which has all of the ideas that Mady and I have been working on over the last year in it, saying how much energy it takes to do all these things. And one of the things that we should all try to do is to limit our shower to something less than, say, 5 minutes. 5 minutes is sort of a max shower. Some people take 10-minute showers, and I was thinking, oh my gosh, not a 10-minute shower. Get them down to 5 minutes, and you'll save a huge amount of energy, both because of the hot water and so forth. So I was thinking this in this framework of minimum shower length, and so I had them do their showers to see how long it took. Well, so I was sitting there teaching the lesson the following week, and I had a little table set up, and we were doing this on Zoom, and I said, all right, tell me the length of your shower. And so they started coming in at 20 minutes,
my
25 minutes. I kept thinking, oh my gosh, what am I going to do? This is not going to be a good lesson for these kids. So I think they were trying to outdo each other with the shower. So that's what we're going to talk about next time. We're going to talk about all the things that we personally do or don't do, and why it matters. That's part of next week. There are also a few things that have to do with the idea of the ethical issues that are involved, the deep ethical issues that are involved in making decisions, and they're not easy decisions. They're not easy to make, and it's not easy to focus on only human beings and human behavior. I mean, how much do we want to restrict our own behaviors when there are things in life which are quite frankly pleasant? We love to do some things, like sit in the shower and just. So, I mean, there are some really interesting issues I think we will talk about next time that have to do with personal behavior and how we respond. So it's going to be focusing on that response rather than on the science. The science, I hope, is okay and understandable, because if you need more devastating talk about things going on around us, I can talk to you about some of my research in soil moisture the fact is that right now the variability, as it's called, the variation in soil moisture in Indiana and Illinois is increasing. And the reason it's increasing is because of the difference in temperature between the Arctic and the mid-latitudes. If you change that temperature difference, which we're doing by heating the Arctic enormously because of climate, because of the CO2 layer, as you know, the Arctic is warming much more quickly than the mid-latitudes. Mid-latitudes going up by a degree, the Arctic is going up by 7 or 8 degrees. Crazy. So that temperature difference drives the jet stream. That's what makes the jet stream go. It's the difference in temperature between the Arctic and where we are, mid-latitudes. If the jet stream slows down, then it begins to meander. It begins to wiggle. Okay, as it wiggles, then you get these periods when the jet stream is suddenly lower than normal, which means you get a lot of rain. It's called flooding. Or it goes up above where it normally is, in which case you get a lot of drying. And so you have what is called mid-continental drought. We live in the mid-continents, lovely folks, and we don't really want periods of a month at a time of no rain and suddenly lots of rain, over rain. That is, you get extremes in both rain and no rain, which you don't want in an agricultural setting. So those are the kinds of things that are important to me, but I think the personal, what I'd like to focus on next time is not the science, but rather our personal response and the moral issues that are involved in that, if you don't mind. I think I have a lot to learn from you. Today I did most of the talking. The next time you're going to do most of the talking. You don't know that, but you are. It'll be good.
Well, thank you very much, Ben.
Great.
Really appreciate it.